Hello everyone, I'm Chuyu from Nanjing University. It is very honor to present our work called DropMonitor, millimeter level sensing for RFID-based infusion drip rate monitoring. This is a joint work with my colleagues and students. Next, I will introduce our work with the following 6 parts. First is motivation. As we all know, intravenous therapy is one of the most commonly used clinical treatment methods in the hospitals. So the drip rate is a very important indicator for infusion monitoring. Improper drip rate may lead to significant problems or even affect the life of patient. Neither fast nor slow drip rate can cause health problems, which are very dangerous for the elder people and infants. Therefore, it is really necessary to satisfy the following 3 requirements: accurate, real-time, and parallel. However, existing drip rate monitor methods usually have these drawbacks. So we want to ask, can we design a battery-free, lightweight, and easy-to-deploy solutions using RFID? Existing RFID-based solutions either sense the liquid or use contact-based solutions to sense the vibrations, so they cannot monitor the drip rate. But DropMonitor can do it. This is a GIF for DropMonitor. We deploy 2 tags beside the drip chamber and propose a log model to distill the drip rate. We can see although the raw signals of the 2 tags are very noisy, our methods can still efficiently extract the correct drip rate. So how to achieve this goal? As we can see, we deploy 2 tags beside the drip chamber for sensing. The signal received by the tag are the summation of the free space signal and the reflected signal. When the droplet falls, the liquid level inside the drip chamber is vibrating, leading to the change of the reflected signals. Then we can extract the drip rate from the signal changes. Based on the principle, we can provide a battery-free, lightweight, and easy-to-deploy way for drip monitoring. To implement the system, we need to address 2 main challenges. The first challenge is how to perform the millimeter level sensing. Particularly, both the falling stage and the vibration stage are millimeter level. So we need to firstly investigate which factor can indicate the droplet falling. To answer the questions, we design 2 isolation experiments and find the vibration of liquid surface can represent the falling of droplet. So we place a tag just above the liquid surface such that the vibration can be efficiently enlarged according to our empirical study. And then we can infer the drip rate from the periodic patterns. For the drip rate inference, we build a signal model in the IQ plane. We can divide the signal received by the tag into the static part and the dynamic part. We focus on the dynamic part, and when the liquid level changes, the dynamic part of the signal changes and rotates in the IQ plane. Based on the understanding, the phase is changed due to the vibration of the liquid level, which means we can use the phase to sense the vibrations. However, in a real sensing scenario, there are lots of multipath interference, especially from the human activities, which are very common in the hospitals. So the second challenge is how to mitigate the multipath interference. We also conduct contract experiments in a real environment and find the multipath interference totally draw out the phase mutations caused by falling droplets. To solve the problem, we deploy 2 tags beside the drip chamber for sensing. One is a sensing tag and the other is a reference tag. Here, based on our understanding, we find the sensing tag can sense both the interference of the human activities and the drip rate signal, while the reference tag only senses interference of the human activities. So, we can compute the difference of these 2 signals from the tag pair to extract the drip rate. After resolving the 2 challenges, we next quickly go over the system design. We have 3 models: signal pre-processing, interference cancellation, and drip rate extraction. For the interference cancellation, we find that each tag is read at different time steps, which can lead to large error when computing the phase difference. To solve the problem, we resample the signal phase into the same sampling time step and then calculate the phase difference. As we can see, after the resampling, the phase change due to human activities can be removed. And then we leverage the frequency features to extract the drip rate. We use autocorrelation to enhance the periodicity. Then we detect the peaks in the correlation sequence and leverage the cluster analysis to estimate the drip rate. Next, we quickly go over the evaluation. We implement the system with impinging radar and layered antenna and evaluate our system with different parameters. We find DropMonitor can achieve the relative error below 2% for drip rate estimation. Moreover, DropMonitor can work well when some bodies are working beside the drip chamber. Last but not least, DropMonitor can simultaneously monitor over 10 users, which guarantees the parallel usage in the hospital. Based on the above system, several hospitals have used our system for several weeks and achieved very stable and reliable performance. We want to see that the deployment of infusion clip is crucial and the liquid level in the drip chamber matters. Finally is a conclusion. In this paper, we present a battery-free, lightweight, and easy-to-deploy solutions to monitor the drip rate. We also design a tech-pair solutions to mitigate the multipath interference and implement the system in real applications. That's all for my presentation. Thank you.